Hello, welcome again to another section of Bed Talks. For my Cinco de Mayo today, I found these beads that I randomly had while cleaning out my room this weekend. So that's what I'm wearing today. Hope you're doing well. So today what we're going to talk about are parametric surfaces and kind of this last little bit here of Calc 3 really, which is really starting to get interesting. So in the first couple of sections here in chapter 16, we tackled understanding how to find, parametrizing a curve, right? We parametrized a curve. Specifically, we had one variable, right? If I have R of t here, this can describe, a way that we can move along a curve specifically, where t had some domain here. Now, what does this say? So this says that I'm a function of just t here, and my x and y move as a function of t together. And so this represented a line or a curve in 1 or 2 or 3 dimensions, depending on how long this was, if I had a z component too. But what if I wanted to go into 3 dimensions? What if I wanted to describe a surface, right? One thing that becomes a little bit difficult there is how do I describe a surface with 2 variables? Do I have to do 2 variables, 3 variables? How many do I need? Well, if a line or a curve is 1 variable, to describe a surface, we need 2 variables here. And so what we're going to talk about today is trying to understand what these parametric surfaces are. So a parametric surface is a surface, we'll call this surface S here, that can be described with 2 variables. We'll call these U and V for the time being, but these can be really any variables that you want. Many times we'll think about these as like theta and Z, or B and theta, or something like that, or X and Y. There's many different types of way you can think about U and V. U and V is just a general idea, a general parameter that we use. And so what we're going to say here is that let's assume that now I'm going to have this function of 2 variables here. And now I'm going to need 3 components. We have x of uv, y of uv, and z of uv. And so here what's going to happen is this will describe a parametric surface where u and v lie in some domain. This little letter right here means in, is a mathematical language for in. So it's just saying that the coordinates uv are in some domain, in this uv domain here. You can think about this as x and y for right now if you wanted to, and kind of imagine that. So we want to find, if I want to describe a surface, for instance, the outside of a cylinder, a plane, a helicoid, like one of a helicoid that kind of goes up like that, maybe a parabolic, a paraboloid or something like that, the outside of a paraboloid. How do I describe these things using 2 variables? And kind of how do I think about that? So what I want to do here, the first couple things is at least to take a look at some examples of parametric surfaces and why do we have them, and maybe how we would want to try to go about, trying to figure out what that would be. So what if I came up with this one? So I have R of uv is equal to something like this, where I have 2 cosine of u, 2 sine of u, and v. And I told you that u ran from 0 to 2 pi. I told you v ran from -1 to 2. I want to try to describe this surface here. Like, what does the surface actually look like? What is this parametric surface? So as a reminder, what we kind of did back in when we were thinking about, if I gave you, a curve in 2 dimensions, right? Something like this up here with my just a curve here, we tried to get rid of the parameters as much as possible, because what that allowed us to do is that allowed us to maybe think of things in x and y, or x, y, and z instead. And because of that, we want to try to do the same exact process here. So what does this actually look like? Well, there's a couple different ways we want to describe these things. I guess the first thing we want to do is note that these are my parametric equations. This is x, this is y, and this is z. So this is saying that x is equal to 2 cosine of u, y is equal to 2 sine of u, and z is equal to v. Now, if I see this cosine of u and sine of u, maybe think about this this parameter being theta, right? This kind of u being theta. And what we can kind of think about, okay, so if I want to try to combine x and y, for instance, here, try to make something, I see trig functions, and I go, oh, okay, well, maybe I want to, square them and add them, because that's a very common technique we like to do, right? So if I do that, if I do x squared plus y squared, I hope you'd agree there would be 2 cosine squared plus 2 sine squared, which would get me 4 because cosine squared plus sine squared would be 1. So what is this? Well, as a reminder, in 3 dimensions, this is exactly a cylinder. This is a cylinder here. That's not too bad. Right, that's a cylinder. So, okay, so what does this actually say? So I have a cylinder in terms of x and y. Now, what is this z doing? Well, this z is just moving. Honestly, it's just moving as its own variable. V is just its own variable, right? So if I keep x and y constant, right, I mean, the z is just going to move. That v variable is just going to move up and down. And at v, you got to think about this z here, right? This is just saying that replacing v with v here, it's just saying that z is between -1 and 2. So maybe more formally, this is just a cylinder, you know, centered around the origin of radius 2 that goes all the way up to z being equal to 2 and z being equal to -1. So like that. And it's not the volume here. We are talking about specifically the surface. It is the outside of the cylinder here. And because z tells me between -1 and 2. So this description right here is a lot easier to think about rather than this. I hope you'd agree. And so because of that, we always want to try to figure out how to go about this. Now, if I did not have this, if I did not know what this looks like, one way to kind of visualize what this might look like is kind of look at something called grid curves. And this is a word that you might have seen in the past in your lectures or something like that. And now grid curves are actually what Mathematica uses for this to plot these things. When you plot a parametric plot, what we'll do in lab in a little bit, what we'll do there is you know, what tries to happen here is a grid curve allows us to maybe start to think about, okay, well, what if I held one of the, how do I draw this thing, right? How do I draw this thing, really? That's honestly what I'm trying to do. I'm trying to figure out if I give you this plot, how do I go about even drawing it? And the idea is with grid curves. So what that means is if I want to find the grid curves with respect to u, let's think about u. What I do is I let v be constant. Okay, so if I let v be constant here, my z is just going to stay the same. Right? My z is staying flat. And if I move u around, I hope you would agree that it's just going to be the circle of x squared plus y squared equals 4, because it's just kind of wrapping around the cylinder. So what that means is I'm going to have grid curves like this. At different, I keep v constant, and I kind of just go around in this direction here. So we see that these grid curves will look something like x squared plus y squared equals 4. They're just circles with a constant v, which means I'm a constant z height. And then lastly here, what my grid curves, I kind of let v be constant. I mean, if I want to try to see what in v, I let u be constant. Now, if I let u be constant here, I hope you'd agree that this means that these two values are going to be constant. X and y will be constant because u is not changing. So I'm staying basically at one of these parts on my circle, right? I'm thinking about, I'm fixing my theta. Right? That's kind of what this is doing. And then what I'm doing is I'm moving v, which is in turn moving z. So what would that look like? Well, that would look like just straight line, right? It's just saying I'm moving z up. I'm not changing x and y. I'm just moving up. And so that's why you'd have these grid curves here. And so combining these two things, we can kind of see as I move u, as I change u, I'm going to have these circles and I'm going to have these lines. So the combination of these circles and lines, you can kind of imagine, would then get me a cylinder. And that's kind of the goal of grid curves in a sense. And it made me start to think about some things that are much more complicated than that, honestly, that are much more complicated, and that might give us some insight as to what's actually happening. So as an example of maybe a type of this, we'll talk about some other more different parametrizations going forward. Once we do some problems, we'll see a couple different types. But that's kind of the goal here. So I want to just do an example of maybe one that maybe you don't know what it looks like, but we can utilize grid curves in itself. So I have something like this, where I have u cosine of v, u sine of v, and v. Okay, So I'm not really given a domain. I'm assuming that I'm running through my U and V for all domains here. Let me just make sure I can write the V correctly. The difference between V's and U's. Boop, 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 boop. Okay. Now this is kind of tough to visualize, honestly. It is. It's not very, very easy for me to visualize. But what am I going to have to do? Well, I'm going to think about, I have X is equal to U cosine of B. I have Y is equal to U sine of B. And I have Z is equal to V itself. Now, let's take U to be a constant. Okay, I'm going to think about my grid curves here. What would my grid curves be? And we're going to try to combine them into one. If U is constant, I'm thinking about my grid curves with respect to V here. Okay. So if I think about respect to V, well, this right here would be a constant. This would be a constant. So you can imagine it would maybe look something like, 2 cosine of V, 2 sine of V, and V. As an example, this is just at least maybe you starting to think about what might happen. And what we see here is that's actually very similar to something we've done in the past, right? If I had cosine of t, sine of t, that's actually a helix. Right? This is actually a helix, which is kind of cool. So what this is going to be, so if U is a constant here, this entire thing is going to be a helix. It's going to just be moving like a DNA that kind of just goes around like that. That's kind of interesting. Now, if I make V be a constant, let's assume now, kind of here, let me do a little bit something different here. Maybe I can make this be pi, for instance. We know that Z is actually going to be a constant, which is kind of interesting, right? Z is actually going to be a constant here because V is constant. So let's make this, something this basic. Let's just make, maybe we can make this a little bit more interesting. Let's just make this, V to be, 0. What if I said that? Actually, I'm going to let this be arbitrary. Okay, I'll let this be arbitrary because I'll show you why in 2 seconds. Sine of B. There's too many special cases, I guess. So we have this, where I have X equals U cosine of B, U equals sine of B, and B. So now, as I hope you'd agree, this means that Z is constant, so we're staying flat on that. But what happened here? Right? What happened here? Well, what I could do then is I could actually solve for U on both sides, right? I could actually solve for U on both sides, and I could get some ratio here, and I could actually get something in relation with X and Y, which is kind of interesting in a way, right? So here, what I could do is this actually becomes, X over cosine of B, assuming that nothing's negative or we don't have any zeros on the bottom. Assume all that for right now. That would be U, and U would also be equal to Y over sine of B. And so since we have U and U here, we actually get, right, if I kind of equate them and I multiply over the sine, I get sine of B over cosine of B times X equal to Y. And so what is this? Well, this is a constant. This is actually a tangent of B, right? And a tangent of B is just some number. So it looks something like Y equals K times X. And if I have something like Y equals K times X here, something like this, if I have something Y equals K times X, this is going to be a line. So think about what's happening here. What this is saying is I have lines going in wherever I keep Z constant. I'm changing the lines there. I'm just keeping that line. That's all I'm doing. I have lines here, and I have a helix here. So I have lines going in the U U direction, whatever this is, this U direction, and then I have, these helices kind of going up like that. So you kind of imagine I'm going to have just these. That's kind of almost a staircase in some way, right? I'm going to have kind of a helix that just kind of just goes out infinitely at every single time. It's just this very flat staircase. And so because of that, we can kind of see what this is going to look like. It's very tough to draw. We're never going to be able to draw these things without help of Mathematica, but it at least helps us to see, why that does. And in Mathematica, you actually see those lines, that mesh point in each one of those. You'll actually see that they're drawing out your grid curve. So it's actually really important to maybe think about that going forward. Okay, enough with that. We have parametrization. And now we'll talk about more parametrizations as we go forward. But when we're coming up with parametrizations, right, it's going to be important for us, at least going forward, to maybe think about something nice. Well, one thing I want to do before we want to get into the next part here, I'll come up with a very easy parametrization. An easy parametrization, if I have something like this, if I have a z which is equal to a function of x and y, again, my goal when I come up with parametrization is always give me two variables that describe every single point on my surface. Okay? Now, it could be any two variables. You can let them be theta and r, you can let them be z and whatever. It doesn't really matter. If you find two, that can work. And parametrizations are not unique. Sometimes it might be beneficial for us to use one situation other than another situation. Maybe I can describe maybe one using cylindrical coordinates, maybe one using Cartesian coordinates. It honestly just depends on the problem and maybe the complicatedness of the problem at our hand. So with this in mind, if I have something like this, what's really nice is I can describe every single point, I hope you'd agree, like this, where I give you the x and y, and then I can give you the z. So in that way, I can actually just describe my parameterization of this surface, whatever this surface is, in terms of x, y, and whatever f of x, y is. It's a very simple parameterization. Maybe this will work well, maybe it won't. It just depends on the domain of the problem itself. Because then you would have, x, y, and some domain d. Maybe that domain d here might be very complicated to write in Cartesian. But this is a way you can do it. This also works for other ways, right? If I had something like x is equal to a function of y and z, you can manipulate this too to make this, okay, well, I can describe all the points in terms of y and z, right? I could do that where I would let x be equal to a function g of y, z, and then this would be y and this would be z. So I can describe all the points this way. So if I have something like it's explicit like that, it may be beneficial for you to do that. So what I want to do now is kind of rotate over to thinking about what we can do with these. The first natural question is, I've defined this surface, right? I've defined this surface. Can I find the area of that surface, the surface area? Like, can I do that? And we can. But I want to do something really interesting. I'm going to actually take this kind of something like this here. I'm going to assume for the time being that I have some function that can be written as x, y, f of xy. Okay, and we're going to manipulate it from there. And then we'll do some problems to kind of understand it. My goal now is to find the area of S. Area of S. What is my area? Okay, what is my area? That is described as r of xy. So what I'm going to do is I'm going to draw something out. When I was taking Calc 3, this was a part where I had some aha moments, especially at the end here. Everything was kind of combining at one point. And it kind of just started to kind of click in a certain way. So my goal for an area here, because we have been including so much here. So let's assume this is like some f of x here. Okay. And I want to find, this is my domain D on the XY plane. Okay. And I want to find the area of this surface right here. And so how can I go about doing that? Well, I have this parametrization R of u v. Okay. Now, what I could do in theory is I could partition this in the x direction. I'm going to do this just so I can show you this. I'm sorry, I'm going to use this as x and y just for the time being, but this all works when I just change this to u and v. It's the same idea. It's a little bit easier to think about in terms of x and y. So I'm going to go ahead and do it in x and y. We'll replace everything with u and v in a little bit. And then I kind of partition everything in the x and I partition everything in the y direction too. Kind of have like a nicely ground stake. So what I want to do, I hope you maybe agree, is my goal is maybe to add up all of these partitioned rectangles. right? The area of those rectangles. If I add all those up, I can get the full area, right? So maybe it should be something like, you know, the integral. It should be a kind of almost a double integral over something. Now, what's that integral over? Well, I need to find the area of this. So how can I find the area of that? Well, if you recall, it's kind of interesting here. So what are 2 points? What are 2 directions? Maybe if I make this really, really small, I can kind of approximate what this is. So if I move in this direction at this point, I'm going to use actually a different color here to highlight it. If I'm at this point right here, and I move in this direction, I'm actually going to start at this point right here. And I move in this direction right here. Okay, I move in this direction. I'm keeping y constant, and I'm moving in the x direction. Well, what direction is that? Well, that's actually just the derivative with respect to x, right? Right, that direction that I'm moving in there is the derivative with respect to x. And it has something of the form, right? It has something of the form like 1, 0, f sub x, something like that. That's that vector right here, and it's kind of moving in that direction. Another way you could think about that, it is the parametrization. We think about, if I take derivatives of this, right? If I take a derivative of a vector, we are thinking that I am taking the derivative on that line of grid curves in some way. If I take r sub x, I'm moving along the grid curve with respect to x. R sub u is moving along the grid curve with respect to u, where I'm thinking that v is a constant. I'm going back to that grid curve idea. I'm letting one of them be a constant. I'm letting that other one, you know, kind of, you know, move in that direction. So if I move here, this vector actually is r sub x. Is the derivative of this with respect to x. Okay. If I move in this direction right here, that derivative is going to be r sub y, right? Because I'm keeping x constant now, and I'm moving y. I'm moving along the grid curves of y, which makes x constant. Now, here's the fun time for you guys to remember something. If I will have 2 vectors, I hope you'd agree that then their vectors then would make this entire rectangle. They would make this like kind of parallelogram, right, out of this. So if I'm making a parallelogram out of 2 vectors, how do I do that? How do I find the area? And the area, as a reminder, is Rx cross Ry. And it's the magnitude of that. So as a reminder, the area of 2 vectors, so kind of, let me just say this. So if I have this as A and this is B, and I make the parallelogram with A and B, the area of this is equal to just the magnitude of A cross B. Harkening back to chapters 12.4, baby. We're going all the way back. That's what's crazy about this. It incorporates everything we ever wanted to know. So with this in mind, we're basically calculating this at every single one of these points. Every single one of these points here, we're making littler rectangles. And if I make littler rectangles and then integrate over the whole XY domain, you can maybe think that in this term, the area of S would then be equal to the double integral of all of these areas, just adding all of them up over this domain D down here. And this is actually how you calculate the area. Now, you might say to yourself, well, what if it's just U and V? The same exact thing. Everything works the exact same way. It's just a little bit easier to visualize when I'm thinking about it in terms of X and Y. And so what I really want to say, just in total here, is that if I have a parametrization R of U V, where U and V live in this domain D, we then can calculate the area of my parametrization. The area of S, you'll sometimes note this as A parentheses S, is equal to the double integral over D of the adding up all of these derivatives. Now, what do I mean by R sub X and R sub Y? Or what do I mean by R sub U and R sub B? What I mean by that is if I have something, if I do R sub U, I take the derivative of each one of the components with respect to that variable, okay? So I need to take derivative with respect to all those variables. And then r sub v would be the derivative of x with respect to v, and so on and so forth. So that's kind of the goal here, to find the area of a parametric surface. It is this formula, and it's not too bad to evaluate. Usually the process is to find the parametrization, if you don't already have it, take the cross product, and so on. Now, I want to just do something really quick, because it's a really, really important fact. What does Rx cross Ry actually mean? Well, would you agree? I'm zooming in right now, kind of doing it like an NCIS kind of thing. If I know that if I kind of make a tangent plane, would you agree that Rx and Ry are both on my plane, my tangent plane? Kind of thinking about it in terms of Fx and Fy, right? They both have to be on my tangent plane. So if I wanted to create a tangent plane, well, I would need to find a normal vector. And this normal vector right here is Rx cross Ry, or more importantly, Ru cross Rv. Aha. And so that's also really important to remind yourself of, is that Ru cross Rv, this guy right here, actually is Ru cross Rv is the normal vector to S. And so if you wanted to create a tangent plane to a specific point, that is the part you use. Okay, that's kind of what you would want to do. So if I have a parametrization, I don't need to go through Fx and Fy, all that. That's not really what I'm trying to do. My normal vector is the cross product between the derivative with respect to u and with respect to v. The kind of the level curves here, the grid curve. Sorry, the level curves. Let's do an example. I'll just practice an example here, kind of thinking about this all together. The first problem I want to do is not too bad, but it's just a really, really interesting part that we'll do. Is I want to find the area of the part of the plane 4x plus 3y plus z is equal to 12 in the first octant. Now, I want you to remember, so I'm trying to find the area. I'm not trying to find volume. You should not be double integrating over anything. I mean, you should not be, finding the volume of anything. We're not doing that. You're trying to find the area of this surface. I'm going to draw this out just to make sure we have this. So to draw this out here, I'm going to use black. Right, what I kind of do is if I want to find the x-intercept, I let y and z be equal to 0. This would make this 4x is equal to 12. And so x is equal to 3. We can do this again and again. For y-intercept, I let x and z be constants, which makes this 3y is equal to 12, which makes x equal to 4, y equal to 4, sorry. And lastly here, the z-intercept is just z equal to 12. So kind of just drawing this. You don't have to do this. I like to do it just always to visualize the problem. I think it's very, very helpful, honestly. The more you can visualize things in this class, the absolutely better. I promise you, especially as we get to this end part here. It becomes very, very, very difficult otherwise. So this is a 4, this is a 3, and this is a 12. And so this surface right here, this part of this almost tetrahedron, this outside of this tetrahedron, this very, very long triangle is my area here. Now, in order to do this, we need a couple things. Firstly, we need a parametrization. To parametrize this surface, I think that probably the most basic one is to think about this in terms of x and y, right? I know what the surface is here. I can describe the surface actually very well with x and y because I know I can solve for z, right? If I solve for z here, and this is what you can see. If I have something of the form, if I get something of the form z equal to something, x equal to something, y equal to something, do it. You get 12 minus 4x minus 3y. And so this surface, describes this part, right? And so in order to create a parametrization, I can just use x and y. And if I then create my parametrization like this, it's going to be x is the x component, y is the y component, and this is my z component. Kind of like that. Now, the important thing to remember here is what is your domain? What is your domain going for? What is your parameter domain? Your parameter domain is this domain down here, right? It's in terms of x and y. That's what it's going to be in terms of. So how can I draw this, right? As a reminder, this is 4, and this is 3. Come down like that. And this is my area. So now, I'm not gonna actually come up with the bounds for this. We'll come up with the bounds later if necessary. But this is my domain D. So I say that X, Y is in this domain D here. You can actually come up with this domain if you want, you know, actually finding this exact line and come up with that domain. Don't do that until you actually have to. And I'll explain what I mean by that. I have some foreshadowing here, at least in my head, that's important to actually think about. But we'll come to that later. Just as a reminder, you need to think about this domain though. The domain here is just, you know, the projection onto the XY plane. Same as what we did in the triple integrals and you know, the double integrals as well. Okay, so then what is the process here? I need to get the magnitude of RU cross RV. In this case, Rx cross Ry. Let's calculate Rx and Ry and then take the cross product of those two things to remind ourselves here. So Rx, the derivative of each one of the components with respect to x. This first one will be 1, this will be 0, and this will be -4. This one, R with respect to y, this will be 0, 1, -3. This is the derivative of each one of these. And so what we do is we do Rx cross Ry, which again is the normal vector to my surface, which is a plane. Huh. What should we expect the normal vector to be? Think about that. Let's see if we're right. I, j, k, -4, 0, 1, -3. You could cross product here. The I component is going to be 0 times -3 minus -4 times 4, which is going to be 4. The j component is going to be a -1 times -3 minus 0. K, sorry, j. And plus the k component, which is just 1 times 1 minus 0 times 0, which is just 1. And so this actually comes out to be 4, 3, 1. And this is my normal vector. Could we have seen this coming? 4, 3, 1. Yeah, we could. The normal vectors make sense, right? The normal vector to this entire surface system makes sense that it's not dependent on anything. Yes, it's just always going to be the same. It's a plane, so it should be the same always, which is great. So you have that. This is nice confirmation here. This doesn't always happen, but for planes, it should always happen like that if you parametrize it like this. So that's at least my opinion. So it's always, that's actually a fact. It's my opinion that you should parametrize it like this. There are some other ways that the book and other places like to parametrize it. I don't. I like to just do it this way because it just makes more sense just in my head. All right, I'm sorry if you hear me drinking. It's just I'm very thirsty at this point. Now, you get it. So I'm now going to try to evaluate this. I now want to calculate. I need to calculate the magnitude of this. Right? That's what I needed. I need to calculate the magnitude. So I'm going to come back up here. I want to calculate the magnitude of this. So the magnitude of RU cross RV. It's okay if, by the way, if this actually is, sorry, the magnitude of Rx cross Ry. It's okay if this is dependent on U and V. It should be for most of these surfaces. In this case, we have a very easy surface, so therefore it's not going to be dependent on U and V. It's going to be just a constant. In this case, this just becomes 4 squared plus 3 squared plus 1 squared, the square of that. 16 plus 25, so 25, sorry, 36, 26. Here, 26, yeah, square root of 26. And so lastly here, if I want to find the area of F, this just becomes the double integral over my domain D, this domain, because it's in terms of my X and Y, of the magnitude of Rx cross Ry, dA, which just becomes square root of 26 times dA. And I can factor out the square root of 26 here, if I can do that. What does this mean? What does that mean? Well, I hope you'd agree, this means just the area of D. And I can do this really easily. It's a triangle. I know how to compute the area of this. Nice. And so because of that, right, I just do 1/2 base times height. This is 1/2 times 3. 1/2 times 3, and my height is 4. And so this whole part over here becomes a 6. And so this becomes 6 times the square root of 26. I don't think square root of 26 can get factored out. No, I can't. And that's my area. That's the area of this triangle in my first octave. And so kind of thinking about the process, we're going to do one more problem, at least with a more complicated one. You know, what you should kind of think about here is, how do I come up with, more specifically, my domain, right? How do I come up with my parametrization? How do I come up with that domain? In this case, my parametrization could be done in X and Y very quickly. And then what we do is we say, okay, well, I need to create my normal vector. My normal vector is Rx cross Ry, Ru cross Rv, depending on your parametrization. And then we kind of just find the magnitude of it. And remember, this case can become really important to remind ourselves that this is just the integral over d. If you didn't realize this, you could come up with the, you know, the integral for this, you know, coming up with the domain, but it's a lot easier to recognize this as the area of your domain. Okay, one last problem here before I head off, at least into, I'm assuming you probably think I live in a white void, and I do. No, I don't live in a white void. I live in this place, whatever this place is. So lastly here, I want to kind of do this problem here to kind of show you. Do I have one other? I think I did. And I just got rid of it, unfortunately. One second. One second here. So I'm going to find, this is the problem that I want to do. Sorry, yep. So I would like to do the sphere of radius A. So I'm going to do 5 here. A here is going to be a sphere. It's going to be actually just a sphere of radius A. So just a random A here, okay? Just some general sphere of radius A. Now, how do I come up with a parametrization of this, right? How do I come up with that? I want to find the surface area of a sphere of radius A. For those of you who know, you probably already know the formula for this. It's like 4 pi r squared. Let's actually try to prove that here more specifically by using this kind of parametrization technique. So if I have a sphere, what is probably the best way to think about it? Well, we know that spherical coordinates are beautiful. They're really, really nice to think about, right? They're really nice. So if I want to come up with spherical coordinates, as a reminder, we let x be equal to rho cosine of theta sine of phi, y equals rho sine of theta sine of phi, and z is equal to rho cosine of phi. Now, on a sphere of radius A, which of these is constant? That's what you always want to think about. When I'm shifting to a different coordinate system, you only need 2 variables. You need 2 variables. So one of them has to be a constant. In this case, what is the constant? Well, my radius is constant because I'm on that sphere, so it's going to be A. And this is how you kind of start to, you know, piece together how you parametrize these things. And this would be A, and A. And then my 2 parameterization variables are theta and phi. So with that in mind, I can actually write that this is R of theta and phi here. I can define it as that. It's just going to be equal to A times cosine of theta sine of phi, A sine of theta sine of phi, and lastly, A cosine of phi. And now what is my parameter domain? For a full sphere, my theta component is my polar angle, so I need the full thing. So I say that theta is between 0 and 2 pi. And phi, we always think about going from the top all the way to the bottom, is from 0 to pi. And now my goal is again to find the area, the surface area of this. So again, what do? I need to kind of do a little bit brute force here. It's going to be a little bit of a tedious calculation, as it sometimes is. But what I need to do now is compute R sub theta and R sub phi. I need to come to the derivative of those two. So I'm going to do R sub theta here. I'm going to go through this. This is going to be a negative A sine of theta sine of phi. I have the derivative of this with respect to theta, so it just goes to that. This will be a cosine of theta sine of phi. And this over here is no dependence on theta, so it becomes a 0. That's going to be helpful in the long run. R sub phi here, this R sub phi is going to become, this will become a cosine of theta cosine of phi. This over here will become negative a sine of theta. Oh, no, sorry, it's still sine of phi, so it'll be just a sine of theta cosine of phi. And this guy, because it's cosine, will become a negative a sine of theta, sine of phi. And now we just have to do the fun interpretation of taking the cross product between these two things. All right, and you take the cross product of these. Now this might become a little bit tedious, but we have just kind of brute force through it the entire time. So I'm just going to do just r theta cross r phi. My x component here is going to be a cosine of theta sine phi multiplied by this guy. So it's going to become a negative a squared cosine of theta sine squared of phi minus, it's going to be this guy, which will be 0. So it just stays like that. The next one, I have to put a minus sign out in front for my cross product. I'm going to get negative a sine of theta sine of phi multiplied by negative a sine of phi here, which will become a squared sine of phi, sine squared of phi, and then we get a sine theta, a squared sine of theta sine squared of phi minus, I get the other component, which is again 0. That's all nice and well. And lastly here, I get this component over here, which I now have to do a little bit more work here. This becomes sine squared of, this way a squared, get negative a squared sine of theta squared, sine phi cosine of phi minus this guy, which is a squared cosine squared sine theta sine phi minus a squared cosine squared theta sine cosine phi, sine of phi cosine of phi. Okay, we have a lot here. This is basically how you do it, and it's slowly gotten less and less. Unfortunately, I'm sorry about that. So what we're going to do here is we can kind of clean this up a little bit. This one here, if you notice, and this is actually what's going to start to become really nice, I hope you will see, is this right here. These sine squared and cosine squared have the same exact terms, so that can get factored out and become a 1. And so this actually just becomes negative a squared sine of phi cosine of phi. And so now I'm going to take the magnitude of this. And this then becomes the square root of each one of these terms squared. So this becomes, I can probably factor out, I hope you would agree, I can just factor out an a squared out of this whole thing. I don't have to worry about that. I can just factor it out. This guy is going to become a cosine squared of theta sine to the 4th of phi. This guy is going to become a sine squared of theta sine to the 4th of phi as well. And lastly, over here, this is going to become a sine squared of phi cosine squared of phi. These guys right here clean up very nicely. I can factor out a sine to the 4th. That's all good and well. I can factor out a sine to the 4th. If I do that, this then becomes just cosine squared plus sine squared, which will be fine, which will be just 1. So this becomes cosine squared. This becomes sine to the 4th of phi plus sine squared of phi cosine squared of phi. We're getting there. This guy now, I can factor out a sine squared, right, from each of these. So I can factor out that fully, and this becomes a sine of phi outside. And this inside becomes a sine squared of phi plus cosine squared of phi. And this is 1. And so therefore, this is my magnitude. Sine of phi times a squared. And lastly here, my area of this surface is then the double integral over my domain D of the magnitude here of this guy, which in this case is just sine of phi times a squared dA. It's very important to note, you don't have to add the rho squared sine of phi here. That's only for volume. And because I've changed variables and done this whole thing, you don't have to do that. It's a really important thing to remember. And so my domain here, I'm only in d rho and d theta and d phi, right? This theta is between 0 and 2 pi. Phi is between 0 and pi. D theta, d phi. That a squared can come out. I'm left with just a 2 pi that kind of just pops out because it's a theta component. And then the sine phi can be integrated to become a negative cosine of phi. Evaluated between 0 and pi. Yeah, something like that. And now what does this become? Well, this becomes then 2 pi a squared. This right here becomes a negative 1, so it's a 1 minus a negative 1. And so therefore we get 4 pi a squared as our answer, which is our answer right here. And that's the surface area we thought about at the beginning. So just kind of taking it back, what did we do? And this is the same process we do all the time. We find a parametrization. In this case, I'm on a sphere. If I'm on a sphere, the most basic one is I know that I can write this in spherical coordinates. So we have to write this in Cartesian or cylindrical, right? I would have so many different movements. I can't really do that very well. So we kind of have to write it this way with terms of theta and phi. I then compute my normal vector. It's pretty tedious here, yes, but it's pretty important to kind of go through it. I compute my normal vector, r theta and r phi. I then calculate the magnitude of it, which comes out very nicely, sine of phi a squared. And then we kind of just integrate over my domain that I come up with, making sure we don't actually have to include that kind of that. But I hope you agree. I hope you see here the rho squared sine of phi that kind of comes up. That's actually where that whole change of variables comes from, actually doing this exact kind of thing. It's called the Jacobian of the matrix. It's fun. Okay, well, that's kind of that. Well, I'll stop here for this video. We're kind of just going backwards here and kind of think about what we did. We thought about grid curves, how we draw them on our domain. I mean, how do we think about these things when I'm thinking about parametrizations? We always need 2 variables. My area can be thought of as the cross product of 2 of my derivative vectors and the norm of that, because that's the idea of area, thinking about vectors back in the day, and going through this whole process here as we kind of discussed. All right, so I will stop there. I hope you are having a good time, and I hope you're staying safe. If you have any questions, let me know. I'm here, and yeah, I will talk to you soon. We'll talk about evaluating some more surfaces over parametric surfaces, and how do we go about that with vector fields. So see you later.